Hello and welcome to the wolfSSL live webinar. Everything you ever wanted to know about how wolfSSL runs on Xilinx. Presented by wolfSSL software developer Jacob. My name is Shizuka and I'll be moderating the webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. If you like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Also, feel free to email us at facts@wolfSSL.com if you have any additional questions. And now I would like to give a brief company overview before we move to the technical presentation. Today, wolfSSL secure over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, most of which are engineers. This progress is, of course, supported by a strong partner network that we are proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, FIPS certification, and FIPS ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfBoot, Java wrappers, and JSSE support, commercial support for Coral, and our latest product offering, wolfHSM. These offerings are accompanied by slow maintenance and support plans up to the 24/7 level. We also offer full service consulting. Before we dive into today's topics, I would like to share an exciting event that we will be attending soon. wolfSSL will be at the AMD Xilinx Security Working Group with location in Longmont, Colorado, Washington, D.C., and Munich, Germany. The first event in Longmont is happening from October 15th to 16th. Be sure to visit us at table number 3 to discuss our latest innovations. And now I would like to turn it over to Jacob to talk about everything you ever wanted to know about how wolfSSL runs on Xilinx.
Thanks, Shizuka. A brief overview of what we'll be going over in the webinar. Building wolfSSL for Xilinx devices. This is different build tools that can be used when building wolfSSL. Some hardware acceleration options that we have. Integration with PetaLinux. This is use with PetaLinux. Also going through the configuration of PetaLinux for how to enable wolfSSL. A little bit about wolfBoot on Xilinx AMD devices, and brief touching on wolfHSM before going into Q&A at the end. So building wolfSSL for Xilinx devices, there's quite a few different hardware devices that we've ran and tested wolfSSL on. We've tested wolfSSL on the MicroBlaze, the FPGA, Zinc, the older Zinc series, the UltraScale Plus versions like ZCU 102, and also Versal SoCs. There are two main ways that wolfSSL is built usually in these projects. One of them is with using auto tools. The other main way that wolfSSL built is with using Xilinx IDE. So this is like something like Vitis IDE that comes directly from Xilinx. Going into a little bit more detail about using auto tools to build wolfSSL for a Xilinx device. So this particular slide is about building for ARM cores. This would be something like the ARC64 or the R5. R5 is used more for like the real-time operations. And then the ARC64 is the more performant, faster CPU that's on the device. One of the ways with auto tools is if you can build it native to the system. This is if you're running something like a Unix-like environment on the hardware and have all of the autoconf tools and make already installed on the device. Then you can just simply unzip wolfSSL, cd into the wolfSSL directory, run configure and make, same as what you would do on like an Ubuntu or any other Unix style environment. Next couple are for cross-compiling. This is more if you have like a trimmed down version of Linux that doesn't have the tools on the device, or even if you're going to be cross-compiling for like a bare metal type of environment. Now, the first thing that you would do is source the tool chain, Xilinx's tool chain. Um, so this one's for Cortex A53, 57, 72. This would be like the ARX64 type of device CPUs. You would run /configure and set the host to ARX64. In this example, I use -Linux -GNU. And one of the nice things about AutoTools is it automatically tries to set the compiler, linker, assembler off of this host string. So that's all you really need is to set this --host equal to ARX64-Linux-GNU and then run make. And the next command I showed that the library that it produced was in fact for an ARX64. This was being built on a x86 machine um, for the ARM ARX64. The command on the bottom here, or the steps on the bottom, I should say, on here are for the Cortex A5, A9. So this is going to be the other CPU that's available on a lot of Xilinx devices. Again, the first step is going to be sourcing the tool chain. This might be in a slightly different path depending on where the Vitis SDK has been installed on the system. But in here it was /tools Xilinx Vitis. Particular version that you're using, this would be something like 2022.1 or 2023. Settings 64.sh. Then in this one, we would use a slightly different host. We'd use ARM, Linux, GNU, EAB, IHF, and make. And then this produces this 32-bit ARM EABI5 version. And I didn't strip out any of the symbols or debug info, so it has that listed on the bottom there, and that display as well. So both of those would produce the respective libwolfSSL that can be linked with the application that is going to be ran on any of those two killer targets, either the ARX64 or the R5s. Next is building wolfSSL for running on MicroBlaze. This is going to be for like the FPGA. The wolfSSL crypto is not rewritten for FPGA, so it's going to be running on like a soft CPU. Performance is commonly slow when running on a MicroBlaze. So a lot of times when people are running wolfSSL in an FPGA, they're looking to do more like just hashing operations or simple AES operations, not the more performance intensive asymmetric operations like signing and verifying. Although we have had a few use cases where people are using those signing, verifying, even up to like a TLS connection in the FPGA. But most of the time, those are on applications where latency isn't as big of an issue, more like internal diagnostics or something along those lines. For cross-compiling for the FPGA, yeah, again, you'd want to source the tools. You want to make sure that the tools are available in the current path. Then this one is a little more involved for the configure used. So again, I set the host, but I set it as none, which means it's not going to be able to it's not going to automatically be able to tag on -GCC here. So we also had to set the compiler with CC equals MB-GCC. One of the other things that I did with this configure is set no wolfSSL dir. This is just to make it so it doesn't look for like durant functions. And then also no socks and wolfSSL user I/O. This is because I didn't have default like TCP sockets. So with this configure, if you were to do TLS connections, you would need to register like a user IO callbacks, that is. And wolfSSL is pretty agnostic as far as the transport medium that we're using. So you could use something like UART or whatever you would prefer to use for the transport medium. I also set it to Little Endian and a few other things such as disabling the file system, then make, and in this one I use read elf instead of file, but you can see that it built it for elf 32 Xilinx MicroBlaze. So if not using auto tools, the other main way that we see people building wolfSSL for Xilinx devices is with the IDE. This is specifically with the Vitis IDE. Detailed steps for building wolfSSL using Xilinx Vitis IDE is actually comes bundled with wolfSSL. So if you look in the IDE directory in Xilinx SDK, there is a couple of example projects, how-to step for actually recreating the projects from scratch. But I'll go through the 2022.1 setup for building wolfSSL, well, actually importing our example project and then building wolfSSL. There, this will be pretty similar for 2023 and newer versions of Vitis. There was a slight um, change from like the older 2019 and before. So we do have, like I said, a couple of different versions in that examples IDE directory. So you can follow one of the earlier versions if you have an older version of Vitis. But in 2022 and later, the first step is opening Vitis and creating a desired platform support. In this one, I was building for a Versal, so I was using the VMK 180. You click on the platform project and set up for the particular hardware that you want to be targeting. The next thing that you would do is enable ZIL Secure and ZIL Mailbox if wishing to use ZIL Secure hardware crypto. Um, and then rebuild it. You wouldn't necessarily need ZIL Secure and ZIL Mailbox enabled at this point. That's just if you're looking to use the Xilinx hardened crypto. And the newer versions of it, such as like on Versal, do have a dependency on ZIL Mailbox. That's because they use like a server client kind of model when communicating down to the CSU. Then in this image here, I show importing, I was building for FreeRTOS in this case, so I imported the two FreeRTOS examples that we have here. But you can see above it, there's two there for a bare metal. So if you wanted to do this process for the bare metal, you would have selected the top two there. And by default, it has the copy projects into workspace. If you've set the workspace up to be in wolfSSL, IDE, Xilinx SDK, and then the particular version of Vitis that you're using, you can remove that copy projects into workspace. It's nice when starting off and testing it to have that workspace location set there because then you don't have to do anything with adjusting the pathing. We have all the paths set relative to the workspace so that it can find like all of the wolfSSL include files and our default user underscore settings .h file. After importing the example projects, what you would then do is double click on the .sprj file, which will bring this pop-up up, and you can then would change the preferred platform. This is just making the imported project use the hardware platform that was set up previously. After that, comes a generation of the linker script and an adjustment of heap stack use as needed. The default heap and stack when generating linker is relatively small. Um, for benchmarking wolfSSL or doing any of the asymmetric uh, operations, you would need to up the heap and stack usage. We give a couple of guideline um, settings, I guess you could call them, for what is expected with at least benchmarking. Um, some of the benchmark heap allocations are quite large, and that's just because it's doing an allocation for the large buffer that it's then going to pass through the crypto operations. Some of our wolfCrypt uh, tests heap allocations are also relatively large and stack usage in there. Sometimes we have like a 4K buffer on the stack. So to make that run smoothly, you have to bump up the stack and heap usage from the defaults. But it's definitely tunable for the particular use case. Again, if you're building wolfSSL just for like hashing or AES operations or something along those lines, you can definitely have it be significantly reduced from what we have in our documentation for stack and heap usage. So after the linker script has been generated and the stack and heap usage is set appropriately, then you can make adjustments to wolfSSL features that are enabled or disabled by altering the user underscore settings.h. By default, our projects are looking for this particular user underscore settings.h. That's just because we've set the relative path to include this particular user underscore settings.h. But that can be adjusted to wherever you'd like it to be looking for the user underscore settings.h. And this user underscore settings.h just includes or just contains a bunch of defines for macros. So it's going to be the particular macros for how wolfSSL is being set up. I also have a redefined for xprintf to zil underscore printf, and that's going to be printouts for things like test case passing or benchmark collection, and using the zil printf, which is just a much lighter weight printf specifically for Xilinx builds. And here you can see I've highlighted the Xilinx script macros. This is going to be for like the ZIL secure um, hardware acceleration support. And then also down here on line 59, this one's for the ARM assembly. It's got to be one or the other. They can't both be defined at the same time. Now I'll go a little bit more into detail about the hardware acceleration builds in a couple of later slides. So that would be it for what's required for building wolfSSL. Pretty straightforward process. You can use the like I mentioned, the auto tools or the IDE. One of the other things that we see in a lot of Xilinx projects is FIPS 140-3 or previously 140-2 certification requirements. There is a FIPS ready bundle of wolfSSL for testing out FIPS integration or going through the certification process and deployment. It's located up on our wolfSSL download page, but it is FIPS 140-3 certified. So we have a certificate number, the 4718, where it's gone through the full certification process. And then it would just be adding your particular operating environment onto that certificate. So building the FIPS ready bundle, the first thing you would do is unzip that GPL v3 version of it if using that for testing it out. Then change directory into it and run a configure enable FIPS equals ready and make. And then this script here, this FIPS dash hash.sh, basically what that's doing is it's updating the integrity check hash that's used. So each time FIPS code starts using the crypto operations, it has to go through an integrity check to make sure that the code hasn't been changed. So basically, it takes this hash and compares it to a new hash of the code before it's used. And this FIPS hash.sh is just an easy script to help update that, and then rebuild it after that hash has been reset. And running wolfCrypt test wolfCrypt would show you the wolfSSL version plus the FIPS module version in use, and then all of the tests that it runs. The next thing we see some on Xilinx devices is our post-quantum use. We have all of the post-quantum algorithm implementations needed for CNSA 2.0. We also, in addition to just having the implementations of those post-quantum algorithms, we have optimizations that have been done for them, specifically in this case on the ARM platforms, which is useful with the Xilinx devices. To configure wolfSSL, at least with auto tools for post-quantum support, you'd want to add the dash dash enable dash experimental, and then the three algorithms that are particularly used, like for the CNSA 2.0, for example, the enable dash Kyber, enable dash LMS, and then enable dash dilithium. For the ARM assembly speedups, you'd want to add dash dash enable dash ARM ASM. I have listed here on Versal because that's what I collected this particular chart from, the numbers from this chart from, but it could also be used on ZCU 102 or any ARM device basically that Xilinx has. You can see the difference between our performance enhancements on ARM for this is for the key generation. In red here, you have 27,000 operations per second versus software only around 19,000 operations per second. And that holds true for all of the different key sizes here. So for hardware acceleration with Xilinx devices, there's two available. One of those being the ARMv8 crypto extensions and Neon instructions. The other one being Xilinx hardened crypto acceleration via the CSU, the configuration security unit. Uh, the hardware acceleration is used to reduce latency. It's also commonly used for offloading the work to free up the CPU for other operations. We have done quite a bit of work with benchmarking with Xilinx. One of the things that we have that's available up on Xilinx website is a white paper from previous benchmark collections. This is a link to that. And that old white paper was on a previous version of wolfSSL, also previous software for Xilinx for the tool chains used and whatnot. But it gives a good demonstration of latency that you can expect and how you can speed up wolfSSL or crypto operations in general by using XilSecure or ARMv8. And also, it highlights a little bit about the trade-off performance on smaller block sizes versus larger block sizes. So there is you got to be a little bit cognizant of tear up or build up and tear down. So in some cases, when you're just processing small chunks of data, the ARMv8 crypto acceleration is going to be much faster. But if you're processing large chunks of data at a time, sometimes the XilSecure is going to win out as far as like performance. Another consideration that people take into account when doing hardware acceleration on Xilinx devices is the isolation of the crypto operations. In some projects, they like using XilSecure just specifically for the isolation, having those crypto operations be isolated to the CSU. So the first one we're taking a little bit more deeper dive into is the ARMv8 assembly operations and making use of the ARM hardware acceleration. This uses, as mentioned, the ARM v8 crypto extensions and the neon instructions. It can be used to increase performance with AES. This is basically all of the AES modes get a performance increase with it. SHA-256, SHA-3 operations, Cha-Cha Poly 1305 uses the some of the neon instructions to help increase performance, as well as the RSA and ECC operations. They use some of the neon instructions. It's enabled with autoconf using that dash dash enable dash arm ASM. Another useful speed up flag is the dash dash enable dash SP dash ASM. In here, SP stands for single precision. So we have a single precision implementation of some of our asymmetric operations like RSA and ECC, which helps get even more performance increases. With an IDE, it is enabled by defining the macro wolfSSL underscore arm ASM. And then I give a couple of SP macros also here, specifically the ARM64. There's a equivalent ARM32 version of it, and then the RSA and ECC macros for turning on the support for the single precision of those. And it's quite a stark contrast between when having the ARM v8 enabled versus just software. This shows some of the AES GCM operations. So with the smaller 128 bit key with AES GCM, you're seeing almost 1,000 megabytes per second. It's around 957. And then in software only, you see a throughput of around 39 megabytes per second. And this is with pretty large data chunks being passed through. It's about a megabyte of data being encrypted and decrypted at a time. Now going over to the other hardware acceleration available on many Xilinx devices is Secure. This is using Xilinx hardened crypto, and the process to build wolfSSL for use for Secure is largely dependent on the OS and hardware being used. And why that is the case is some of the hardware has permissions level limitations on the addresses to access and actually directly interact with the CSU, part of that isolation of the crypto operations. So for PetaLinux, there's this AFALG interface that is being used. That's similar to what AFALG would be in just like any kind of Linux environment. And they use that same framework for interacting with a driver to then communicate down to the CSU and get results. With wolfSSL, to enable talking with that interface, it would be ./configure dash dash enable dash AFLG equals Xilinx. And then we would try and use the Xilinx drivers using the AFLG interface. For free RTOS, it's commonly using the Vitis IDE for setting up projects to use Secure. That's the most straightforward way. You could probably do something with CMake and Auto Tools, but for using Secure with wolfSSL, the path most commonly used is with the Vitis IDE, at least for free RTOS. Then for using Secure with bare metal builds, you could do either compiling from the command line or use of the Vitis IDE. We have examples in our IDE Xilinx SDK directory with using for the building wolfSSL for the bare metal bare metal environments, but it would be relatively straightforward from the command line as well. And this could even be using something like an HSI kind of instruction and downloading. Xilinx has up on their GitHub account embedded SW, which has a subdirectory of software underscore services, SW underscore services, which lists all of the libraries that they have. And in there, you could get the Secure, the most recent Secure source code actually, and be able to compile it and build it that way. So with AES-GCM, wolfSSL can make use of different types of key locations that you may have. One of those being if you're just using a software key, but we can also make use of the device key with AES-GCM operations. So when initially setting up the wolfSSL AES struct, you'd use something like x secure underscore CSU underscore AES underscore key source underscore dev. And this macro is actually coming from something like the x parameters.h. So this is coming from one of the Xilinx header files. And when passed it to our AES GCM set key, we know to then just make when we're interacting with ZIL we know then to just use the device key for encryption and decryption. We additionally support TRNG and ECC use with the Versal board. So that was one of the changes from ZCU 102 going over to the Versal boards is they added in more crypto operations. Mm, Some of those being TRNG and ECC. They also expanded like the AES-GCM key sizes supported. But wolfSSL supports everything available on the Versal board with ZIL. We also support both the client server model with newer boards and ZIL versions, along with older style ZIL APIs. We've been integrated and used with ZIL for quite a number of years now. So we have support for the older versions of ZIL along with support for the newer client server model. Moving on to PetaLinux. When building PetaLinux and wanting to use something like ZIL Secure, you can double check that. Well, the first thing would be to double check that the hardware acceleration support is enabled. And that can be done with this command, the PetaLinux -config-c kernel, then going into the cryptographic API and hardware crypto devices. You can see here that RSA, AES, and SHA-3 was enabled. This is for a ZCU 102. That's why it only has the three listed there, but it's just the RSA, yeah, AES, GCM, and SHA-3 384. Another thing that was added to PetaLinux that makes it additionally, I guess, a little bit easier for getting wolfSSL in the root file system is there was a configure option added in around PetaLinux 2023. It was mid to late versions of PetaLinux 2023. And to enable use of the new wolfSSL option, you can do PetaLinux-config files fs-c and then navigate to the file system packages. We're in libs network, and then there's wolfSSL there. They also have the option to be able to default turn on ARMv8 crypto acceleration. That's what this additional crypto option below here is. And that would increase the performance greatly as seen before with the AES GCM comparison on the ARX64 devices. So all of that was building the wolfSSL library and different hardware acceleration options that are available with wolfSSL and Xilinx devices. These next couple of slides are talking about our wolfBoot option, and this is going to be like a secure bootloader. wolfBoot support for Xilinx UltraScale Plus was initially added in 2020, so it's been around for 4 years now. And it is a direct U-boot replacement from Proof Security. Although it is a direct replacement for U-boot, it can be used as a second stage boot as well, if wanting to keep some of the U-boot features around. wolfBoot provides enhanced features compared to U-boot, such as firmware integrity and signature verification on boot. It also provides image integrity checking with a use of a hash, validation of the signature using ECC RSA. And where it's using wolfCrypt, it can use some of the post-quantum algorithms as well for validation of the signature. So it could use something like LMS or XMSs. It supports multiple boot partition support. And one of the really nice features is a rollback to last known working or fail-safe image on failure. And this is nice because it helps prevent bricking devices by some kind of mistake when updating the firmware. Some of the one of the examples of building for Zinc MP is available with actually bundled with wolfBoot. So it's got a config examples directory, and there's a config in there specifically for Zinc MP. There's, in addition to that example listed earlier, there's a full example for building with the Xilinx SDK. This would be with Vitis and integrating into the first stage bootloader chain of trust. Also creation of the flash boot.bin image with boot.bif and bootgen. So basically everything you need to get up and running, put it on an SD card, put it on the device and boot up. And that is located in IDE Xilinx SDK directory bundled with wolfBoot. So it's a very similar named directory as what would be in wolfSSL, only this time we're looking in wolfBoot. Additional wolfBoot features supports the quad SPI, SDMC, EMCC boot support. It also has 32 and 64 ELF loader support, flattened device tree support for fix-ups, and AX64 EL1, EL3 support. And the last wolfSSL product for running on Xilinx devices I'll touch on briefly here is wolfHSM. Shizuka had made mention that we're having a initial release here shortly. It's one of our new products that we've come out with. And wolfHSM provides a portable and open source abstraction to hardware cryptography, non-volatile memory, and isolated secure processing. Since using wolfCrypt, it has the option for post-quantum algorithms and FIPS 140-3 certification. There's also the potential for using the server side isolated on an FPGA or either in one of the ARM trust zones. But it's set up more like a client server kind of setup where it has a client side and user land communicating with some kind of server side that's interacting with an HSM or either a software HSM itself. So that goes over a lot of how wolfSSL is running on Xilinx devices, how to build wolfSSL, some of our other products such as wolfBoot, how it integrates right after the first stage bootloader, provides a secure boot up, location of our examples, and yeah, what's upcoming with the Wolf HSM. And at this time, I'd like to go ahead and open it up to if there's any questions that people might have.
Thank you, Jacob. There is a question. What are people using for a source of entropy on ZCU 102 boards?
Yeah, it's a great question. As I'd mentioned, the TRNG was introduced on Versal boards, so that's one of the newer one. But back on the older devices, there wasn't really a good source of entropy, TRNG available. Some people use like a third-party IP that runs in the FPGA that gives a source of entropy. But other people have looked at our Wolf Rand product. So it uses kind of like one of the jitter the jitter algorithm for generating a source of entropy. So Wolf Rand could potentially be a solution for people on something like a ZCU 102 or some other device that doesn't have a built-in TRNG.
Awesome. There's another question. How big is wolfSSL's memory footprint when used on Xilinx hardware?
Yeah, wolfSSL is very modular. There's a caveat with the answer is it depends on what you're building wolfSSL for, because you can build out specific features that may be unwanted, such as like RSA or ECC capabilities. If looking at like TLS connections, it usually runs around like 30K for heap or stack usage. Um, and then the code footprint size, again, it depends on the build of wolfSSL. The SP most performant builds with single precision, it takes a little bit more code size than a trimmed down version where it's less performant.
Okay, perfect. That is, I do have a last question. Have the other wolfSSL products been used on Xilinx devices?
Yeah, it's a good question. I had just mentioned wolfSSL, wolfBoot, and wolfHSM, but we do have quite a few other products that we've seen people use on Xilinx devices. One of them that comes to mind is wolfTPM. So interacting with TPMs on Xilinx hardware, sometimes people would use wolfTPM. Um, most of I would say most of our products have been tested and ran on Xilinx devices, including our SSH implementation, Wolf SSH.
Okay, thank you for answering that question. And thank you again, Jacob, for hosting the informative webinar and everybody for joining today. And please don't forget to follow us on X at wolfSSL as well as our LinkedIn and YouTube channel. If you have any further questions, please email us at facts@wolfSSL.com. Thank you again and see you next week for automotive hardware security module functionality design and application on October 7th. Thank you.